Let's do another calorimetry example. In this example, 50 milliliters of 0.100 molar silver nitrate and 50 milliliters of 0.100 molar HCl are mixed. They're mixed in a calorimeter, and the following net reaction results. The silver ions interact with the chloride ions to precipitate out silver chloride solid. Okay, this is a classic precipitation reaction, and it's balanced as written. And I'm leaving out the spectator ions of nitrate and the protons, the H plus ions. The initial temperature of both solutions is 22.6 degrees Celsius. The final temperature after mixing is 23.4 degrees Celsius. So the temperature has gone up. I would like you to assume that the density of the solutions is 1.0 gram per milliliter. You can also assume that the specific heat of the solutions is equivalent to the specific heat of water, which is 4.18 joules per gram degree Celsius. Using all of this information, calculate delta H, the change in enthalpy, for the reaction in kilojoules per mole of silver chloride that forms. All right, so you should definitely pause the video and take a moment to write down that question and think about how you're going to solve it. There's a lot of information here. I would like to start by focusing on the fact that we're going to need to figure out per mole of AgCl formed. So we're going to have to look at this equation and try to figure out what's going on here. We are mixing silver nitrate and HCl, and it looks like we're mixing them in equimolar quantities, right? If I multiply the volume by the concentration, it's going to be the same numbers in both cases. So I can take either one of those quantities to calculate the number of moles of silver chloride that I'm forming, because I'm going to have 50 milliliters. I'm going to convert that to liters, 0.050 liters of the silver. I could also say of the chloride, since they're the same, there's the same volume of both solutions. And I'm going to multiply that by the concentration, which is 0.100 moles of silver chloride, silver nitrate rather, per liter. Then I need to look at the balanced reaction. Okay, so if I have a certain molarity of this stuff, it's going to give me the same molarity of the solid because I have a 1-to-1 ratio in that balanced reaction. So I have 1 mole of silver chloride being precipitated for every mole of Ag plus ion that I'm adding. So if I do all of that, I should get 5.5 times 10 to the minus 3 moles of silver chloride. And I could have also done that using the concentration of the HCl solution as well. Since they're equimolar, it doesn't matter which reactant I use. So, figured out the moles of silver chloride that I'm dealing with. Now I need to figure out what the change in enthalpy is going to be for the reaction using the things that I know from the problem. So I know that the definition of delta H is that it's heat flow at constant pressure. Heat flow at constant pressure. I have constant pressure here. They haven't said anything about pressure, and in most laboratory settings, the pressure is constant. And I know that I can take the heat capacity and multiply it by the change in temperature, as long as I'm careful about the units. And I am here again at constant pressure, to figure out what the Q is. So I have the heat capacity of the solutions, right? It's 4.18 joule per gram degree Celsius. And I always put this in quotation marks because when I plug in 4.18 joules per gram degree Celsius, I cannot forget that I need to get rid of those grams from the bottom by multiplying by the amount of solution that I have. Okay, and I want to be very careful to specify what I'm talking about here. The density of the solutions is 1 gram per milliliter. The specific heat of the solutions is equivalent to the specific heat of water. So how many grams of solution do I have? That's the question I need to ask in order to figure out what to multiply this by. How many grams of solution do I have? Well, I have 50 milliliters of one and 50 milliliters of the other, and I know their density is 1 gram per milliliter. So 100 milliliters total if I'm adding them together. And at 1 gram per milliliter, that gives me 100 grams of solution. Okay, 100 milliliters of solution is going to be 100 grams because I'm assuming that the density is 1 gram per milliliter. So I'm going to multiply this by 100 grams of solution, and that will enable me to cancel out the grams. The final thing I need to figure out is how to get rid of the degrees Celsius. So I need to figure out what delta T is. Delta T is equal to T final minus T initial. So looking at this problem, I start at 22.6 degrees and I end up at 23.4 degrees Celsius. So I can use those two values to figure out the delta T. 23.4 degrees Celsius minus 22.6 degrees Celsius is a difference of 0.8 degrees Celsius. So I'm increasing, the temperature of the solution is increasing by that much, 0.8 degrees Celsius. So that means I can cancel out my degrees Celsius. Remember, always plug in delta T, not an initial or a final value. And this gives me a total of about 300 joules for my delta H, or my Q value. Okay, now I need to figure out delta H per mole. So I'm going to put that 300 joules over the number of moles that I calculated of silver chloride, which is 5 times 10 to the minus 3 moles. However, I need to think about what sign to put here. I know that the solution is getting warmer. The solution here is the surroundings because the reaction is actually the system. Okay, so this reaction that I wrote down here, this is the system, and the water around it, the solvent basically, is the surroundings. And it's the water that I calculated the 300 joules for, right? The water is heating up. The solution is heating up. The solution is the surroundings here. So that if the solution is getting warmer, I have to be careful here. I want to calculate the delta H for the reaction. So the reaction is the system. That means that from the point of view of the system, this delta H is negative. The solution is getting warmer, so the reaction is exothermic. And from the point of view of the system, the delta H is negative. The heat is flowing from the reaction into the surrounding solution. So that means this delta H is going to be negative 60,000 joules per mole. And I would change the unit to scale the unit up a bit to call this minus 60 kilojoules per mole. Okay, and that's, again, it's an exothermic reaction from the point of view of the system. So you're going to see this over and over again. It's going to be a theme in calorimetry that any heat gained by the solution, so the solution is the surroundings. You can think of it as the solvent, since solution is mostly solvent, but really it's the solution that is the surroundings, is due to heat that is lost by the reaction. by the reaction. So the reaction is the system and the solution is the surroundings. And you're going to see that over and over again. So you really, really need to think about your signs. Okay, so here in this example, since the heat was gained by the solution and lost by the system, uh, this implies that the delta H of the reaction is going to be negative. And if the solution got colder, it would be the opposite. It would be because the reaction had a positive delta H. Okay, and again, there are two types of reactions from a calorimetric point of view. There are exothermic reactions and endothermic reactions. And exothermic reactions have negative changes in enthalpy. So that negative sign implies that heat is flowing from the system to the surroundings. Okay, because it's all the sign convention is always from the point of view of the system. And that is like the example that we just saw. The opposite situation would be called an endothermic reaction. So that means that we're putting energy into the reaction. And an endothermic reaction is always going to have a positive delta H. Endothermic reactions have heat flowing into the system from the surroundings. So in that case, if we had a solution like this one and the solution got colder, it would be because the system, the reaction, is sucking heat out of the solution. So that would be an endothermic reaction.